So I'm Rojar Haddadian. I'll talk about the wavelet in this session of the SDLET time, which is going to be the last one of 2018 SDLET time. And feel free to interrupt me at any time if you have any question. So let's see what is wavelet at first. So wavelet is just a transformation of the time series. You had seen time series yesterday. So we can transform any time series to the wavelets. Wavelets are like the Fourier series and transforms of the time series, and they are highly functional tools with valuable properties. There are different applications of the wavelets, and we will see a couple of them today. And the term wavelets itself was coined in the geophysics literature in 1982. And let's start the wavelet with the just simple wavelets that we usually call it Haar wavelet. To make a this Haar wavelet, we need to know what is the multi-scale transform. So when we transfer the time series to the wavelet, then we transfer it to different levels. So we'll see how we can make those different levels by multi-scale transform. So any problem in statistics arises in a sequences of the data observation. That's why we choose, instead of having a functional wavelet, I prefer to present it as a sequence rather the function. And the other reason is that I'm going to use the R. So an R is illustrated, it's more useful with the discrete sequences. So let's assume we have the vector of y1 to yn, and which is a vector of the time series. And now we wanted to transfer this to the wavelet. So first of all, there are some assumptions in the wavelets. At some point, these are required, but you can eliminate this later. This assumption, like the length of the wavelets should be equal to the 2 to the power of j when j is an integer number. But it's possible to eliminate this later. But this is just for simplifying the mathematical notation of wavelet transformation. So suppose we have the time series of y1 to yn, and now we wanted to make the different levels of the wavelet. First of all, we looked at the first step, we look at the difference of each observation of y with the previous one. But be careful, we are looking at just disjoint pairs of them. So the second one minus the first one, fourth one minus the third one, and so on. The next step, which is pretty similar to the previous one, now instead of looking at their differences, we just sum them up. So instead of looking at the difference of each pair, now we sum them up. So the first level of the wavelet is actually the first differences. Now the second part, in the second step, we'll sum them. We look at the summation of each pairs, and then we continue to do the same procedure. Next, find the differences between the first levels of the C coefficients that we found them, and then repeat this to find the summation of them. So let's see an example with the example. So it's basically just a combination of these two ways of adding up or looking at the difference of each pairs. So we make the levels of the wavelets of any time series using this summation and the differences. Let's see an example. With the example, it's going to be pretty much easier to understand. So suppose we have the y, the time series or sequence of the data set with the length of 8. So notice that here j is equal to 3, which is 2 to the power of 3 equal to 8. So that assumption is satisfied here. So the first level, we said, looking at each pairs and the differences between them, and the differences between them. So 1 minus 1 is 0, 9 minus 7 is 2, and so on. And then next, this is going to be the first level of your wavelet transformation. Next, we sum up this, the second step of the wavelet transformation. So 1 plus 1 is 2, 7 plus 9 is 16, and so on. We call this as a further coefficients, okay? So the actual wavelet coefficients are these, the i's coefficients, the levels, which we generated them based on the differences. But then the next step, having this summation, we can look at the differences at this level. So differences of 16 minus 2 is 14, 14 minus 10 is 4, and so on. We can keep continue this to get the zero level of the coefficients or further coefficients. So the procedure that we explained, we usually call it discrete wavelet transformation. Just as a recall, we call the coefficients of D that they were generated based on the differences. We call them detailed coefficients or wavelet coefficients. And the CJs are the further wavelet or scaling coefficients. We know that based on this procedure, we can reverse back any wavelets to the time series. So when we have the wavelets, when we transfer the time series to the wavelet, we can reverse it back to the original time series. Let's see an example first, see a demo, and then I'll go back to the okay. So first of all, I'm using the package of wavetrash. There are many packages. I will just name a couple of them later at the end of the presentation. But I'm using the functions based on this package today. So let's library and then going back to the example that we have. So that's the same sequence of the numbers that we had in the presentation. And just to make the levels of the wavelets, the command is just WD, just discrete wavelet, with the filter number of the one and the family of this. That's gonna just generate the discrete wavelet transformation for you. Now, I will show it to you. Okay. So now let's see what we have in YWD in the wavelet transformation. Let's just see what we have here. So you can see that the result is a list of 8 values. So it shows that we have the discrete wavelet transformation, and we have the C, which are the further coefficients, and D. The levels that we have are 3 levels, 2 to the power of 3. Remember, that's equal to the length of the data set, which was 8. And the type of the wavelet that we had was the Haar wavelet and the other things. So now let's see what we stored in that list of 8. So we have the C coefficients, D levels, and so on. So let's see, for example, if we wanted to just extract the further coefficients, we can see the further coefficients, including the original sequence of the data sets that we had. And but if you notice that, so we said 1 plus 1 should be 2. Notice this, it's not 2. It's different from 2. Why? Because it's Haar wavelet. What is Haar wavelet? Since we wanted to, okay, let's go back to the presentation. So when we transform the time series to the wavelet, we wanted to keep the properties the similar and the same as original time series. So if we look at the length of the time series or energy or norm of the time series for the original sequence that we had, it was 219. But when we transformed it to the wavelet coefficients, now the norm or the size of the, or the energy, they call it sometimes energy in geophysics, it's much greater than the original norm. So, but we need to normalize the discrete wavelet to keep this norm be equal to the original length or original norm of the time series. That's why we divide the each differences by the square root of the 2. So we have some coefficients, some value, some constant value, just to multiply every wavelet coefficients by that one to keep the norm be the same as the original time series norm. So we can write this procedure just in a general mathematical notation that we call it Haar wavelets. So now we can see that why the value that we had in the original time in the demo or further coefficients is not equal to 2. It's actually 2 divided by square root of the 2. And we can also extract the same. We can extract the actual wavelet coefficients, or we can even extract any specific level of that, not all of them together. So we can specify which level we wanted to see instead of reporting all of them, just reporting the level 2 of the wavelet coefficients, or just level 1. Yes. I will do that. And so again, you can recall any specific level from the further wavelets, similar thing. And so you can basically call any results that you have in this list. And we can plot the wavelet coefficients. So these are the wavelet coefficients. You can see that plot. So it doesn't look nice here because it's just a sequence of 8 numbers, but we will see later. Let's zoom this plot. But at least we can see that we have the 0 level of the coefficients, the wavelet coefficients, the second level, and the third level. And we can see that the magnitude of this vertical bars actually shows the magnitude or the size of the wavelet coefficients. Okay, so this one represents the higher wavelet, the larger wavelet coefficient. And again, as I said, we can reverse back the wavelet just using WR function. We can reverse it back to the original time series. So we can see that now we have the original time series based on the just reversing back the wavelet levels. Let's see an example. So this is just a simulated data set, again, stored in the wave trace package. We can plot the data set and see that it's just a chirp noise simulated. And then we can see that this is actually a time series. Now let's see if we wanted to make a discrete wavelet transformation, how the plot of this wavelet coefficients will look like. So similar comments, just for that one. Sorry, I reversed it back. So these are this plot shows the wavelet coefficients of that time series. You can see that the number of the levels increased because the length of the time series increased. So 2 to the power of j, remember that 2 to the power of j is equal to the length of the data set. So the length of the data set here is 2 to the power of 9 because we have 9 levels of the data set. So basically, if we just start from the 0 level and having just one of the further coefficients, then we can reverse back the wavelet transformation to the time series, which again, we can use the WR command to reverse back to the original time series. Any question up to this point? Okay. So there is another type of the wavelet transformation. So up to here, we just looked at the discrete wavelet transformation, the basic one, which is that the other name for it is just decimated wavelet transformation. But there is another type that we call it non-decimated wavelet transformation. Let's see what is non-decimated wavelet transformation. Okay. So for the non-decimated wavelet transformation, yes. Mm-hmm. Okay, let's go back to that. Oops, what happened here? Firefox is already on. Okay. I don't care about the Firefox. Okay, here. So here in the plot, this is what you mean. So we can see that here, this value. So you don't see the exact value of the coefficients here, but the vertical bars, this shows you if that value is the large value or small one. But you stored all the coefficients in that list of 8 numbers that you have. You have the value of all the 8. So the plot just shows the different location for just summing them or adding, like the trees that we had here in the presentation. It just shows. Let me go back to the example that we had here. This is just a simple wavelet transformation. If you just consider the D coefficients, ignore the other coefficients. The plot just shows the D coefficients and not even showing the numbers. It just shows these numbers with the just small vertical bar, like and that one, if it's getting larger, that just shows, for example, this one is larger than this one. Okay, and if and they all are on the horizontal line, and it's considered, if it is positive, then it goes up, otherwise it goes negative. It's really hard to understand anything from the plot of the wavelets. Okay, but sometimes when you have the seasonal time series, you will see that it shows the seasonality in the time series. We will see that. Okay, but at least you can see again here, it shows one seasonality here. It shows this pattern, or it's the other way of showing the time series. But you can't interpret anything from the plot exactly. So for the non-decimated wavelet transformation, if you remember, for the Haar wavelets, as I said, we looked at the disjoint pairs. Now, even if instead of looking at the disjoint pairs, we look at every single combination of the pairs and looking at their differences. So y2 minus y1, y3 minus y2, not so. Remember, in the decimated one, we just skipped this one. We didn't have this one in our coefficients because we said we look at the disjoint one. But here for the non-decimated one, we actually consider every combination of the wavelets, even the last one minus the first one. It's going to be like a circle. Okay, and but we will see what's the difference between you can see that right now the non-decimated one is not the orthogonal wavelet transformation because they are not independent from each other anymore. The first coefficient is dependent on the second one, third one dependent on the second one, and so on. They are not independent, but in the decimated one, they were independent. So the non-decimated one is actually more useful. It has more information for the time series analysis, especially for the non-stationary time series. Some people call the non-decimated wavelet transformation as a stationary wavelet transformation, which is not a good name because it's more applicable for the non-stationary time series. Yeah, but let's look at the non-decimated plot for this same wavelet that we had. Non-decimated one is better for the non-stationary time series. But some people call it stationary wavelet, which is not a good name for that. And that's why here we can see that in the type of the function, even when you wanted to do the non-decimated, the only changes you wanted to do is changing the filter number to 2, and the type is going to be station. But that's a non-decimated time series and a non-decimated wavelet, which is more applicable for the non-stationary time series. Don't be confused with this. And then we can see that now the non-decimated wavelet shows more pattern of the time series, shows more like seasonality of the time series that we had. So it has more information. It's more like the continuous coefficients because we looked at each specific pairs of the differences. There is another way that we can show the non-decimated times wavelet transformation, and some people call that as a. So they separate the even and non and odd coefficients from each other, and they call it packet. They call it packet wavelet transformation. So it's again non-stationary, non-decimated, but it's like, okay, let's see. Here, for example, go back to the example that we had. Oops. Okay. Here, to the example, go back to the example. So if this is the decimated wavelet, then we have y2 minus 1, y4 minus 3, and so on. But for the non-decimated, we have all of them. And if they are in order and we have all of them in order, then that's just the non-decimated wavelet transformation. But if we keep the odd and even differences, odd and even coefficients separately and represent them in a separate plot, then we call that packet. So let's go back to see how. So this is the non-decimated representation of the wavelets, and then this is just the packet. We can see that at each level we have two different coefficients. This is like the left one is for the odd one and the right one is for the even coefficients. So it looks at both of them and it's a non-decimated but just separated the even from the odd one. Another application, let's see the first application of the wavelet that people call it wavelet shrinkage. Let's see what is wavelet shrinkage. Assume that we have we see it sequential of time series of yi, but we know that this time series is based on the another function g of xi plus some noises, and we are interested to estimate this actual gxi, not in yi. We are seeing yi, so in other words, we wanted to denoise or filter out the noise from the original time series. So what we see, yi have some noises, and we wanted to estimate the actual time series without noise or filtering out. The word that people are using in wavelet is wavelet shrinkage for this method. But there are some assumptions for this method. The first one is, it might be the first assumption is that the noise are independent independent, and having a normal distribution with the mean of 0 and variance of fixed variance value of sigma square. Or it might be just a white noise that they are independent with the same constant variance, not following the normal distribution. It might follow any distribution, but just having a constant variance with the 0 mean, and they are independent. So again, what is wavelet shrinkage? We observe a function contaminated with the additive noise. We take the wavelet transform. We wanted to filter out the noises from the wavelet levels and then reverse it back to the original time series. Any question? No? Okay, let's see the demo of this wavelet shrinkage. This is another data set, again, simulated data set for the blocks, bumps that is stored in the wave trash package. Let's see the original plot of this wavelet, which is like this. Now, what I want to do is adding some noises to this time series and then try to filtering out the noises using the wavelet method. So I find the standard deviation of the bumps, and this is just the way that I added the noises to the original time series that I had. And okay. And then I generated the errors, the noises from the normal distribution with the mean of 0 and the constant of signal to noise that I considered for that. I assume the signal to noise ratio is 2. So now I created the time series of Y with the noises, adding this time series with just some noises. Let's see now what's Y. Okay, so we can see that we added just some noises to the bumps that we had. Okay, let's see first again, how does the wavelets of the bumps look like? So this is the wavelets of the exact bumps that we had. And this is the wavelets of the wavelet transformation of the bumps with noises. Okay, so if we compare these two, we can see that here in the lower level, for the actual bumps that we had, actual time series of the bumps that we had, this is like more flat values with just small, pretty small, that shows pretty small noises in that. But when I added the noises, now you can see that some differences here. It's not flat anymore. So we can see that the noises are more in the high levels of the wavelets. So if we wanted to filtering out, if we assume that this is the original time series that we observed and we wanted to denoising that, then we need to filter out the high levels of the wavelets. Now let's see how we can do that. There are different ways to do that. One of them is the universal threshold. So we can define the universal threshold is just, again, remember we could access the level of the coefficients of the wavelets. So I'm going to just get the last level of the coefficients, which is actually this level. I'm going to just get this coefficients and then subtract the actual time series minus this one. So we can, and then I use the median absolute deviation of the finest level, and then find the threshold based on this, and then we define the threshold of the wavelets based on the universal time threshold that we defined it actually. And then now this is the wavelets filtering out the noises based on the universal threshold that we had. And then now I'm going to reverse it back to the time series. let's make a plot for that. So I reverse it back. I make a plot for the reversed time series and then plot the actual bumps that we had. We can see that this is not a good way because the estimated, actually the estimated value that we had for the bumps, just make it again, just to be clear. So the estimated one is pretty much less than the actual value. So we can see that this universal threshold is not a good way for filtering out the noise of this time series. There is another way that we call it cross-validated thresholding. So just using the threshold function, you can just change the policy to the cross-validation and then use the MAD as a deviation, which is mean absolute deviation. So again, we can reverse this back and then plot the reverse, the denoised or shrinkage wavelets transform versus the actual one. So there are different ways that we can define this, but the best one, so this is level by level one, and the best one so far I figured out is this false discovery rate. So based on this, you can mention that what is the level of the false discovery that you wanted to denoise it or filtering out from your original time series. So again, you just need to change the policy to the false discovery rate, and then if you are interested in the actual theory behind this method, is you can look at this reference. And again, let's plot it versus the actual one. So you can see that there are different ways for the thresholding, but there is no way to say that one of this is going to be best one for all the time series. You need to try it for different time series and denoising them, and like maybe using a training and testing, finding which one of this filtering is better. So based on this, you can filtering out or shrinkage your wavelets and reverse it back to the original time series without the noises. Any question up to here? You can change this. You can do it by level by level, or universal. Okay. So by changing this, you can have it if by level is equal to false or true, you can have in universal or level by level one. Okay. So another application of the wavelet could be just transforming the images to the wavelets, which is a 2-dimension wavelet. We don't have time to cover that today. You have seen the basic transformation of the time series to the wavelet levels, which was just a 1-dimensional wavelet, but it's possible to transform any pictures to the wavelets. So for this example, we can see that if this is the actual picture that we have, the top right one, this one, shows actually the fine scale of the wavelet coefficients. It's just a plot based on the fine scale, which is the lowest one, then the highest one, which is for example, in our example, which was the 9th level. Okay, the highest level of which shows the details. You can see that the picture has the details of the pattern. But then the bottom left, it's just the medium scale, just the picture based on the medium scale of the coefficients. And this one is the coarse scale, which is the low scale of the coefficients, and which shows the vague picture of that. And we can see that when we add up the coefficients, we can reverse back again the time series, the plot of the the coefficients of the plot or any pictures to the actual one. So this is the wavelet. The top right one is the wavelet approximation, which for the finest level, which is the summation of all the coefficients that we have for the wavelet. And you can see that it's actually the actual picture that we had. It's exactly the same. But if we just looking at the medium scale of the approximation, which is just the low levels up to the medium scale, then we have some sort of, again, picture similar to the actual one with some noise, with the less details of that. And the coarse scale is going to be just a vague picture of the, shows the vague picture of the original picture. So that's another application of the wavelets. You can transform any picture or images. It could be applicable in the image processing as well. These are the references I used in my presentation. Basically, this textbook has most of the functions, comments based on the wave trace package. And this textbook explains the theory of the wavelets pretty well if you are interested in that. I found different packages, some of them just recently published, like I think I can't click on this. I had a link on that. I will change the plot, this PDF. Maybe you can open the link. I can't open the link here. But these are the available packages in R for the wavelets. I'm pretty sure there are many, many more if you just search on Google. But I think wavelet comp is more for the images. Any question? Okay, that's all for today. Thank you.